Good afternoon, everybody, and welcome back. Today, I'd actually like to introduce you to Pradeep Lall of Auburn University. He'll be presenting updates regarding his task, ART-001, Characterization of Emerging Technologies in Military Systems. With that, Pradeep, I'd like it if you could turn on your camera and please take it away from here.
Thank you for that introduction, James. Good afternoon. This is task ART-001. The title is Characterization of Emerging Technologies in Military Systems. The sponsor is CCDC AC. My name is Pradeep Lall. I'm the McFarland Endowed Distinguished Professor at Auburn University. My primary appointment is in the Department of Mechanical Engineering. I have a joint courtesy appointment in the Department of Electrical and Computer Engineering. I'm also director of the NSF Cave 3 Electronics Research Center here at Auburn University. And the research team that's working on the program is a part of the Cave 3 Research Center. So with that said, what are the emerging technologies we are talking about? There are two categories or subtasks that we'll present updates on today. The first one is on interconnect methods, in which we'll speak about lead-free electronics and solder interconnects under high strain rate operation and sustained high and low temperature thermal storage. There are a number of dope solder alloys and wire interconnects that have emerged in this particular space. And in the harsh environment applications, much of the electronics may be subjected to strain rates in the range of 1 to 100 per second and sustained low temperature down to negative 65 degrees centigrade, sustained high temperature up to plus 200 degrees centigrade, and prolonged storage up to 1 year. A second subtask deals with prognostic health management methods and the development of early indicators for identification of impending failure. Both subtasks are responsive to the ability to mitigate risk with usage of these newer interconnect technologies, newer materials that have entered this particular interconnect space. So with that said, the motivation for working on this task is that in aerospace and defense systems, the electronics may be exposed to extremes of temperatures, and the extremes of temperatures may range from negative 65 to plus 200 degrees centigrade. Plus, everything that's manufactured actually may not get deployed almost immediately. Things may be stored for a prolonged period of time, and therefore there may be a sustained period of aging in non-climate controlled enclosures that the electronics may be stored in. In addition to that, the electronics may be subjected to high strain rates that may range into in the neighborhood of 1 to 100 per second, and these strain rates may be encountered during storage, transport, and deployment of the systems themselves. The big technology gap in this area is that a lot of the newer alloys and the newer interconnect methods that are entering this particular space are leading the development of tools, and the development of tools is somewhat lagging. So our ability to be able to assess reliability and our ability to be able to mitigate risk is somewhat limited with usage of these newer materials and newer interconnect methods in the next generation programs. Now, from a solder alloy standpoint, the solder balls may be at multiple levels in an electronic package. They may be from between the package and the board. They may be between the chip and the substrate, depending on the package architectures. One may have wire interconnects as well in some of the packaging architectures, which also are transitioning from gold to copper as well. So in order to develop tools for mitigation of risk, the first subtask actually deals with measurement and characterization of the material data and creation of some foundational data sets that would be used to develop reliability prediction models under overlapping stresses of temperature and vibration. So it's a combination of high strain rate and temperature, and the temperature occurs a couple of different times in this presentation. Firstly, it occurs as a preconditioning method where parts may be stored for a prolonged period of time. A second way that temperature occurs is during operation, which means that the temperature of operation of the part may itself be vastly different. So the way the samples are created, that actually we are creating uniaxial tensile samples. One is shown right here at the bottom left. And the way we do that is by using glass tubes. So we melt the solder alloy that we are trying to study. Most of these are advanced doped solder alloys. That's what the industry is migrating to for a number of reasons. And these are starting to appear in many of the commercial parts as well. So we have worked with a number of companies to actually procure these alloys. We melt them in this crucible that has a heating coil around it. The temperature is monitored by a temperature controller. We have a glass tube that's attached to the end of a rubber tubing that's connected to a vacuum pump, and then the solder is actually sucked into the glass tubing to form the specimen. So once the specimen has solidified, then we'll send it through reflow. This is a typical reflow profile that the specimen would go through. And once it's gone through reflow, to be able to replicate the grain and phase structure in an actual package, we would then X-ray it and make sure that the specimen is free of defects. And the idea is to create a thickness of the specimen that's about the same order of magnitude or similar in dimension to that of a solder joint, a package level solder joint. Although the width and length are larger, but the thickness is very similar to that of an actual joint. These are some of the test conditions that we are studying. As I mentioned, there are a couple of different temperatures that occur in this test. So first set of temperatures are operating temperatures. They range from -65 to +200. We are also looking at a second temperature, which is the storage temperature for sustained thermal storage, and that is 100 degrees centigrade. For most part, we also are taking data on 50 degrees centigrade. Number of different alloys that are being studied in this program. So SAC305, SAC-Q, SAC-R, and there are a few others that actually we won't talk about today. These are further along, and that's what we have more data on. That's what we'll focus our presentation today on as well. 4 different discrete strain rates, 10, 35, 50, and 75. So for each of the different strain rates, what we have done is we have measured a stress strain curve, and that's what a typical stress strain curve would look like. We are plotting the measured stress that's acquired from the force measurement of the load cell, and then we are measuring strain using both optical methods and mechanical methods such as LVDT, linear voltage displacement transducer, that's in our frame. The data has been acquired at a bunch of different temperatures. So here we are looking at data from 25 to 200 degrees centigrade. And what you notice is as the operating temperature increases, the ultimate tensile strength of the material actually successively drops. The elastic modulus changes as well. Now, if I scan the graphs from the left to the right, both in the top row and the bottom row, one can see that as the strain rate changes from 10 to 35, from 35 to 50, 50 to 75, my ultimate tensile strength is going up, which basically means my threshold to failure is increasing with the increase in strain rate. Also, my effective modulus is changing, which means my structural stiffness of the alloy is changing as well. And we are comparing this versus pristine set of curves, and that's what these brackets indicate. So you can actually see that curves actually start to migrate down with just 30 days of sustained operation at 100 degrees centigrade. So the next 3 slides actually are somewhat of a pseudo movie. So I'll flip through them so you can actually see what's happening with the curves, and they're at 60 and 90 days successively. And so you can actually see how the curves behave. So this is 60 days, and that's 120 days, excuse me, not 90 days, 120 days. And so if I was to go through and flip again, you can actually see as I go from 30 to 60 to 120, the curves successively migrate downwards, which basically indicates that the ultimate tensile strength is evolving, the effective modulus is evolving, and the material behavior is continuously changing as well. And the brackets here indicate the effect of the sustained storage temperature. These curves are at 100 degrees centigrade, but if they were at 50, that's where the curves are. And that's data also that's been taken earlier on in the study. So now I'm going to change gears. I'm going to talk about SAC-Q. So these are color-coded. The prior graphs were black in color in the title, and these are red. So that tells you we have shifted alloys. And here, the data has been taken over the entire temperature range that I talked about at the beginning of the presentation, which is from -65 to +200 degrees centigrade. And so you can actually see a similar effect exists for SAC-Q as well, where as I increase the operating temperature, my ultimate tensile strength is dropping. And as I increase the strain rate, my UTS is increasing, and so is my effective stiffness. And again, if I go from 60 days to 90 days, I can actually see the curves actually migrate downwards. And so the similar effect that I pointed out to you in the case of SAC305 also exists in case of SAC-Q. So one thing that we would recognize is that the material behavior is continuously evolving. And how does one then capture the entire material behavior in a computational framework that would allow us to simulate the reliability of these packaging architectures under overlapping stresses and be able to predict life and be able to assess risk with the usage of these newer doped alloys in these harsh environments. So the way we have approached the problem is to use of a model called Anand viscoplasticity model. This is a model that actually models both the plasticity and the viscous behavior of the material. And the advantage of using the Anand viscoplasticity model is that it's available as a standard offering in a number of commercial codes such as ANSYS. So if one actually was able to scale the model to represent the material behavior over the entire range of strain rates tested, over the entire range of operating temperatures, over the entire range of sustained storage temperatures, then perhaps one can actually model these assemblies as well. So most of us are familiar with Hooke's law. Stress is directly proportional to strain in Hooke's law, and we generally use something called the elastic modulus. But because this is a nonlinear material, we are going to start off with a stress equation that kind of looks like a pseudo Hooke's law, sigma is equal to Cs, where C here, instead of being the elastic modulus, is a parameter that depends on strain rate and temperature. So you can see the form of C here. S, instead of being strain, is an internal variable called that represents deformation resistance of the material. And so if one takes the form for C and plugs this into this equation, one can formulate the equation for stress as a function of strain rate, temperature, and the internal deformation resistance. One can then mesh that with the evolution equation. And if one integrates the evolution equation, substitutes the saturation value of the evolution equation, and substitutes the stress equation that one computed earlier, one can actually formulate a material equation that looks something like this. And this is for the one-dimensional case. The true package deformation behavior is a three-dimensional scenario where the material could be subjected to stresses and strains along all three orthogonal directions. So the way to capture the material behavior in this computational framework is to be able to fit this material law to the entire set of data that I was showing you earlier on. And the way one does that is by fitting the 9 constants that characterize this particular constitutive equation. And that's what we have done as a part of this exercise. So these are the 9 constants that represent the material behavior. And what we have done is we have fit these constants for each duration of thermal storage. So for 30 days, there's one set of constants, 60, 90, 120 days. So each set of constants represents one duration of thermal storage for the material in its end application. Now, one thing that's very important to point out is that as an analyst, one is generally used to having one set of material properties. And at the beginning of the analysis, you want to be able to put that into a computer model and say, okay, I want to be able to simulate a phenomena such as thermal cycling or shock or vibration that the electronic assembly may be subjected to. And those material properties more or less stay constant throughout the simulation. They are the ones that the analyst would put in right at the front end of the analysis when one starts the simulation. In this case, what we are trying to show is that the material properties actually do evolve as a function of time. And the longer that the duration of the simulation that one's trying to simulate and trying to replicate in a computational virtual platform, the material properties are going to be significantly different from that for the pristine material. And so that's something that one has to be cognizant of, and one can't take the properties as being constant as a function of time through the simulation. So this is for SAC305. The same process has been done for SAC-Q. So we have a set of material constants versus different durations of isothermal storage. The intent is to actually capture this data for up to 1 year of thermal storage to replicate the risk with using some of these newer doped alloys in the end application. But right now we have about 90 days of data that the samples have been tested for. The remaining samples are in test right now, where they are in thermal chambers for extraction at the end of the year, at the end of the 1 year period, and then they'll go into test. So this is an ongoing test, and we are presenting an interim snapshot of our progress. So then the next question that one has to assess is, how well does this set of material constants actually represent the original data set that we started off with over a range of aging conditions, over a range of operating conditions, over a range of strain rates. So what we have then done is we have taken these constants that we developed and fit to the material model and said, okay, I'm going to just go ahead and simulate the high strain rate uniaxial tensile test and see how well the material actually replicates the behavior that I started off with. So what this shows is, James, I'm getting a message saying broadcast has ended. Are we still live?
So I'm going to have to go and double check that. I just saw that message too. Give me
You are live.
Still live. Perfect. All right.
All right. Thank you. So we have created what's called a daisy chain board assembly. So it has 12 packages. These are identical packages. All of them have the alloys that we are testing. There's a single board assembly for each alloy. So there's one for SAC305. There's one for each of the alloys that we are looking at. We have created a model for this board assembly as well. So that's the actual physical board assembly. And because this is a dynamic simulation, the one thing that we want to be able to do is we want to be able to check and see if the weight of the final assemblies in both the virtual platform, which is the simulated model, and the physical platform are identical. So that's kind of what this shows right here. The weight is identical, and although this font's kind of smaller to read, if you were to zoom in, you'll find that this is very similar in weight to the simulated weight as well. So simultaneously, what we have also done is we have subjected the board assemblies to a sustained period of thermal storage, and that's why you see a slightly darker green color because of extended thermal storage. These assemblies have then been mounted on a electrodynamic shaker. So that's the inside of the chamber. So there's a thermal chamber around the shaker that allows us to run the shaker at a variety of temperatures up to 300 degrees centigrade, although the data that I'll show you today is for up to 155 degrees centigrade. So the board assemblies are daisy chain, as I mentioned. So these wires are the daisy chain assembly wires. And what we are doing is we are actually measuring the resistance in situ during the exposure to overlapping stresses of temperature and vibration, and logging the data using a data acquisition system. And then we log the time to failure as well. So here, I'll show you first data on SAC105. So this is at 5G. So each of the rows is at a different temperature. The first row is at 25 degrees centigrade. The second row is at 55 degrees centigrade. The third row is at 155 degrees centigrade. So if I was to actually compare what each of the rows shows, first thing I can see is the leftmost column. This is U1. This is the corner package right here. The rightmost column is U6, which is closer to the center, which is right here. So if I was to compare each column, I can see that as I increase the temperature, my graphs keep moving to the left, which basically says that my time to failure is reducing with the increase in temperature at the same G level. So that's takeaway number one. Secondly, if I was to compare these graphs amongst each other, the time to failure varies as a function of location, which is unique to vibration. Generally speaking, in a thermal exposure, you would not have that because that's a more isothermal form of stress, but in vibration and in, more importantly, overlapping temperature vibration, you would expect that much more frequently. So that's the second thing that you would see as well. And if I scan this bottom row from the left to the right, my time to failure is changing as a function of location as well. So the next graph, this is on SAC305, similar effect. If I was to compare each column, the graphs slide to the left with increase in temperature, and again, different time to failure as I scan from the left to the right in the bottom row, and I can also easily see that as I move to the center, my time to failure drops as well. So what we have then done is we have simulated, so that was experimental data. We have simulated the board assembly with the various package elements. So you can actually see the electronic molding compound, the chip, you can see the substrate, you can see the various interconnects. These are solder joints that have been modeled as Timoshenko beam elements in the global model. And then we've done a local model with the brick elements as well. So then we impose a high G load on the model. And then we actually extract what's called the hysteresis loop. So larger values of the hysteresis loop correspond to a higher amount of plastic work. So that's basically shows two things. First, the size of the hysteresis loop changes between 5G and 10G. Higher G levels result in a larger hysteresis loop. So that's intuitively does make sense. If one looks at the board, these magenta color this magenta color rectangle corresponds to this arrangement of the hysteresis loops. So this is U1, that is U2, and you can actually match the other part locations pretty easily using that process. And so what one can see is as I move from the support, this is where the board is supported. These are the corner locations. Closer to the center, the size of the hysteresis loop goes up. And that holds true both for 10G and for 5G. So that tells us that the damage is accrued faster in the center locations, which is again what we saw here as well, where the time to failure was lower in the center location compared to the corners. So from that standpoint, the model captures the experimental data extremely well. So what we hope to be able to do is we hope to be able to take these hysteresis loops and mesh them with damage relationships to be able to predict life. So that's something that's still work in progress, and that has yet to be done. And once we have that, we'd be able to now predict life based on the amount of plastic work accrued per cycle of high temperature vibration. So let me shift gears. I'm going to talk about the second subtask. So we'd like to be able to predict life, but we'd also like to be able to mitigate risk using PHM, or prognostic health management. And the idea is to be able to step into the pre-failure space and see if one can identify impending failure. So get an early identification of failure prior to catastrophic failure happen. So meaningful replacement or repair can take place prior to a catastrophic failure of the system. And the way we are approaching this is through identification and measurement of leading indicators of impending failure. And these are indicators that we have developed here as a part of this particular program. And we'll share with you how well some of these indicators work and which are the ones that we worked on that actually didn't work out so well. And there's some learning in that as well. We'll share with you the effect of the sensitivity of sensor location and the few feature vectors and the embeddings that we have studied. So there are quite a few approaches to do PHM. So we've kind of broadly categorized them here. So there are other researchers that have looked at physics of failure-based approaches. There are teams that have worked on data-driven approaches. We have done that too. Some of our prior work has relied on resistance spectroscopy, also on strain measurements. And there are also other model-based approaches that exist in open literature as well. In this particular case, we are somewhat relying on the reliability physics. So it's a combination of a physical measurement in addition to understanding the progression of failure based on feature vector embedding that we have developed. So from that standpoint, it's somewhat of a hybrid approach compared to the ones that I have listed here on the screen. So we have two different board assemblies. One is a single component board, and what we have done is we have sensorized the board, so you can actually see the various strain gauge locations. There's a strain gauge rosette that's labeled C1 through C3, single strain gauge C4. There's a strain gauge C5 and C6 closer to the support locations to look at the impact of the sensor location on the feature vector. So it's very hard to, in an actual board assembly, know where to put the sensor, because one really doesn't know where the failure is going to occur. So one of the big tasks that we undertook was to see, hey, what if I don't know where the failure is, and I was to rely on a network of sensors at various locations to be able to determine if I can still identify impending failure. So that's basically the intent of that exercise. The assembly is mounted on an electrodynamic shaker. That's what you see here inside a thermal chamber. We are actually sweeping in a tiny range of 330 to 350 hertz. And that's because the natural frequency of the assembly is 340 hertz. So since we are testing a large number of board assemblies in this program, each one of them is slightly different. So therefore, instead of exciting at a single frequency, we are trying to do it in a narrow range of frequencies to be able to not vary the test protocol from board to board. So this is the single component board. This is the multi-component board. Similar protocol in terms of sensors, some on the part, some on the board. Similar range of sine sweep, different natural frequency owing to the different mass and different stiffness of the board. But there are 12 parts instead of just a single part. And you can actually see these are daisy chain, and you can see the daisy chain wires as well. So we connect that to a data acquisition system, and we are acquiring strain data and continuity data simultaneously at a very high sampling rate. We test the assembly through the initiation of the test all the way till failure and beyond failure actually as well, because not all the parts in a multi-part board fail at the same time. So we continue to test till everything has failed. So that's the reason why we have these color-coded. Reds are before failure, the blues are after failure. So for most part, we have relied on spectral domain analysis. So we take time domain data from the various sensors, and I've already highlighted where the sensor locations are. So that's what the time domain data looks like. So that's for board 1, that's for board 2, time domain data. And you can actually see what the time domain amplitude looks like. There we have a peak closer to the natural frequency as the frequency sweep is going on in that narrow window. We take that information into frequency domain, and we can, the tool that we have used is the discrete Fourier transform. And so there are 50 data sets throughout the lifetime of the board assembly that we just progress through failure till after failure. And so these are the various sensor locations. So if I was to compare different sensor locations, first thing I see is if I were to just take an FFT, I actually don't see very much difference visually. So what we have done is we have tried to segment the data into a narrower band, looking at a band of 500 to 3000 hertz. And if I step forward in time, so this is 1 minute data. If I step forward in time to 40 minutes, now I can actually start to see features. And there's a variance between the different sensors. There's also changes between before and before failure and close to failure. Failure happens close to 450 minutes for this particular board assembly, as I will show you in a few moments. So you can actually see that the feature vector actually changes before and close to failure. Similar changes, C5 through C8. You can also see the variance between the different sensor locations as well. So then we have formulated two different feature vectors. The first one is based on principal component analysis of the FFT of the strain signal. The second is based on the PCA analysis of the instantaneous frequency. So we basically take the time domain signal, take it into frequency domain, compute the instantaneous phase, compute the instantaneous frequency, use the instantaneous frequency PCA analysis to be able to create the feature vector embedding. So that's basically kind of what we are doing. So now if I plot the feature vector in the feature space, so that's my principal component space. Ideally, I want assemblies with different amount of accrued damage in different parts of the feature space. So the reds are in different locations than blues. Reds are before failure, blues are after failure. So you can actually pretty clearly see that one can actually put the feature space put the parts with different amount of accrued damage in different parts of the feature space. Second thing that one can see is actually that if one looks at the variance of the PCA components, the variance actually increases tremendously prior to failure. So the dashed line is prior to failure, and the variance increases tremendously prior to failure. So that's extremely helpful. So the variance is a good indication of impending failure. So similar trends in feature vector 2, occupy different parts of the feature space, similar increase in the variance prior to failure. So feature vector 1 and 2 work extremely well in this particular case. So I can see them side by side. I can look at the increase in variance prior to failure. So the left one's based on FFT PCA, the right one's based on PCA of the IF. So then what we did was we wanted to look at, well, what about the shear components? Do shear components provide us initial additional insight beyond the initial insight that we developed using the normal components of strain? So these are the normal component variances. So they still look great from the strain rosette, but the shear components actually don't. So our variance actually increases after the failure time. So shear components actually are not very valuable from our standpoint. Either they increase after failure or they increase much before failure and still spike after failure. So they are not good candidates for feature vectors. So in the spirit of full disclosure, we are sharing with you what worked, but also what didn't work. Analysis 2, we looked at normal strains again. So this is C4 again. If I start to look at now single sensors at slightly different locations, here the instantaneous frequency in our analysis and testing was the more robust feature vector formulation as compared to the FFT based. So here the FFT based feature vector actually fails, but the IF still succeeds. So that's the advantage of using the IF based PCA. So here similar effect on C5. So this is further out. So you can actually see I can sense the increase in variance. So even when the sensor is fairly farther away, IF still works, although FFT does not perform that well. So this is definitely the more robust embedding that we identified in our work. So now if I get really far away, C6, which is close to the support location, here now none of the feature vectors actually work very well. So when I get very far away from the point of interest, that does end up being a problem. So this is C7 on top of the package, and none of the feature vectors actually work very well if we were to actually print sensors on top of the packages to be examined. So that's not a good location for placement of a sensor for PHM purposes, at least in our experience from this standpoint. Similar thing on C8, a lot of noise here in the IF based feature vector, and the FFT based feature vector on top of the package does not work either. So then we started to look at, well, how does the board assembly fare if we had multiple failures occur? So does our fidelity go down if multiple failures are accrued on other parts, but not the part of interest, so to speak? So that's kind of what we are showing here, where 2 parts have failed in case 1, 7 parts have failed in case 2 out of the 12.
So Pradeep,
and the IF,
I'm just interjecting to give you a 5-minute warning.
Yeah, I'm on my second to last slide. But thanks for the heads up. So one can actually see the variance increase just prior to failure for the IF-based feature vector, and I can see both C2 and C4 exhibit that behavior and the ability to identify impending failure. So with that, I'd like to summarize. So what we have done is we have shared with you data on 2 subtasks. The first one being high strain rate properties after prolonged storage, where we shared with you data on a number of different advanced lead-free alloys at high strain rates in the range of temperatures of -65 to +200 degrees centigrade, and we shared with you a method to actually model the constitutive behavior using a non-viscoplasticity. We also shared with you how the model would be implemented for assessment of the transient dynamic behavior of board assemblies in harsh environments under overlapping stresses of temperature and vibration, and we showed how to create the hysteresis loops. In a second subtask, we shared with you the development of feature vectors. We shared with you two feature vectors, one based on PCA of FFT, the second based on PCA of IF. We shared with you how well these feature vectors work, in what cases they do work, what cases they don't, and which of the two is more robust for exposure of board assemblies and identification of early impending failure under overlapping temperature and vibration. So with that, I'll stop. Thank you for your attention, and I'm happy to take any questions if you have any.
So Pradeep, thank you so much for the talk. I know that this kind of maybe falls outside of the research a little bit, but any of the, from what you've looked at, does any of it actually apply to a more dynamic use case? And what I mean by that is that something has been in storage for some time, it then gets taken out and used, but then gets put back in storage. Is there any kind of reliability metrics that can be placed on something that's been used? So now the temperature is like fluctuated and now it goes back into storage?
So yeah, that's a great question, James. Actually, so that's a more complex case. So where we would have multiple exposures of thermal storage and multiple exposures of high strain rate harsh environments. In our case, what we assumed was there was the initial storage when the assembly was pristine, it was new, it was stored prior to deployment, and once it was deployed, it basically was used till end of life or wear out. But you're correct that may not be the case. Assemblies may come out of storage, they may be deployed, they may go into storage, and then they may be deployed again. And that's a much more complex case, which requires us to actually do something called cumulative damage assessment. And that's somewhat further down. We do not have actually even base damage relationships in this particular space. So that's a technology gap under overlapping stresses. So as a part of this task, what we hope to be able to do is identify methods to be able to assess damage under overlapping stresses. Once we have a good handle on that as a part of ART-001, then perhaps in a follow-on task that we might propose, we may start to look at sequential damage of the kind that you're proposing, where there may be multiple exposures. How does one accumulate damage? Can one resequence the damage where one can take all the thermal aging exposures, steady state exposures, put them into one and resequence the entire history and equivalence them to what we have and come away with still a reasonable estimate? The answer is I don't know yet, because we don't have that data, and neither does it exist in open literature. So so that's still an open question, but that's I think what we can say today.
Pradeep, thank you so much. I actually have more questions, but we only have about 30 seconds. So let me thank everybody for attending, and I hope to see them in the next session. Pradeep, as a personal note, though, I'm happy we finally got to meet sort of face to face.
Yeah, likewise, James.
Yeah, Pradeep has been doing work for quite some time, so really it's very, very, very interesting. So I encourage everybody to kind of go over and take a look and see. It's very interesting. And with that, thank you all, and see you soon.
Thank you.